will broadcast them from the chat box.
That's
Yeah,
fine, because I
yeah.
can't see the chat box. Yeah.
No, no, I can see the chat box,
Okay.
and at the end we will have person-to-person discussion.
That's fine. I will lead the presentation mode, so I'll see
Yeah,
people.
yeah,
That's good.
yeah. Okay. Okay, so welcome to IIT Bombay Virtual Competitive Algebra Seminar. We are very happy to have Professor Tony Iarrobino from Northeastern University. He will speak on Jordan type and Lefschetz property for Artinian algebras. So over to you, Tony.
Thank you. Thank you very much for the invitation. I really appreciate it. I met Professor Verma some time ago in, I think, 1996 in Hanoi. And then Claire de Cruz was a postdoc at Northeastern, I think soon after that. So I'm certainly very pleased to I've never been physically in Mumbai, but very pleased to be here. And thanks for adjusting the time. So this, I understood this to be a talk sort of for beginners. So please excuse if you already know everything here, probably not everything. But so I have a lot of slides, 39, but I won't go my colleagues who are Pedro and, you don't need the abstract, Pedro and Macias Marquez and Chris McDaniel, who give the reference for most of this, told me it was a bit long, and but I could cut out certain sections. So the goal is to introduce Jordan type and Jordan degree type for Artinian algebras as invariants that generalize the more well-known weak and strong Lefschetz properties. There was a book, which you see in reference to there, which was the Lefschetz properties, which came out in 2013 by a whole group of people led by Junso Watanabe, which is a basic reference in the field, but more about the Lefschetz properties, a little bit less about the Jordan type. I want to state some results and some sources and mention that there's some open problems. So here's a plan, introduction, Macaulay duality, the Jordan degree type, some questions that people can work on, free extensions, which I might have to pass over, and strong Lefschetz and tensor products, and then some more questions in 7 and 8. Kind of an interesting application of something quite different, non-graded Gorenstein algebras. So the first point is that if L is an element and the maximal ideal of an Artinian algebra, if the algebra is graded, that would be in, you know, in A1 direct sum A2 direct sum A3. We'll mostly in the first part of the talk about graded Artinian algebras, but sometimes I'll say maximal ideal, and that will also apply to local situations. There's a multiplication map just from A to A, and that's nilpotent because it's an Artinian algebra. So that means that, and L belongs to maximal ideal. So that means that the Jordan block decomposition is just a partition, telling you the size of the blocks. It's a partition of n, which is the dimension of the algebra. So A doesn't have to be standard graded. We say a strong Lefschetz if there's a linear form such that partition is the same as the conjugate of the Hilbert function. I'll show a picture of that in a moment. For a local, we say that it has strong Lefschetz type also if the same condition is held. Weak Lefschetz turns out to be the same as that the number of parts of the Jordan type is the same as the Spurner number, which is just the maximum value of the Hilbert function. And there's a proposition. This is HW refers to this Spring Election Notes 2080. In proposition 3.5, it says graded unimodal, then A is weak Lefschetz if and only if the multiplication maps have maximal rank, multiplication by L in each degree. So here's an example. I'm taking n greater equal to 3. look at the ring k of xy, y x squared xy, y to the n. Its Hilbert function is 1 to 1 up to 1n minus 1 in degree n minus 1. So these are the strings. By strings, I multiply by y. So 1 goes to y to the n minus 1. And then x goes to 0 because xy is in the ideal. So the partition that corresponds turns out to be n1. Well, that's kind of automatic because I got a really long string, and when I find that I can write the space A as a direct sum of these strings where the last yn minus 1 goes to 0, then that's a unique partition. So if I view this as a partition on the Hilbert function, then its partition is 1, 1, 1, 1, and then a 2. But if the conjugate of that is n1, which is py, so ay is strong Lefschetz. I'll do a picture of that next slide. So on the other hand, px, the multiplication by x, is the opposite, because the strings are 1 go to x goes to 0, x squared is 0, and then all the powers of y multiplied by x are 0. So that has n plus 1 parts. The Sperner number, which is the biggest value of the Hilbert function, is 2. So the pair ax is not even weak Lefschetz. So here's a picture of that. Let's see, I took one case, y4. So the Hilbert function is 1, 2, 1, 1, 1. The conjugate of the Hilbert function, when regarded as a partition, is 5, 1. And that was just the strings for the multiplication by y, or by x plus y for that matter. The Jordan degree type, which I'll introduce formally a little bit later. Oh, by the way, please feel free to say I'm going too fast or going too slow and boring people, or if I should take more pause in between slides.
This is fine.
Okay, yeah. Thank you. So the Jordan degree type adds some information. I'll define it formally later. But you add the information about the initial degrees of the strings. So for this particular example, actually, I can actually point using this thing, but then it makes a big mess. I better not do it. Now let's see if I can click that.
Tony, Y4, Y4 is a generator.
God damn, what was that?
YQ.
Okay, I want to go back to view full screen. Yeah, I think I should. So I'm not sure why that's coming on.
Yeah, this is fine. But Y4
good.
Is not a generator, no?
So, yeah, just stay where I'm doing it. I know how to, okay. So in this particular case, the Jordan degree type has a 5, the length 5 string with a 0 because it starts in degree 0, and a length 1 string, which is x to 0, starts in degree 1. So the next basic type is Macaulay duality. I would think that many people are very familiar with this. So you let one ring act on another ring by contraction or differentiation. But contraction is a little simpler for what we're doing. Contraction works better in characteristic P. So that's xi to the u acting on capital Xj to the v is essentially the derivative without the coefficient. And then you extend bilinearly. And the theorem of Macaulay is that there is, though he may not have said it exactly in this phrasing, there's a one-to-one isomorphism between the set of graded AG. What is this? I don't know why my computer. Okay, let's stop you. Okay, sorry. My printer decided that it wanted to, on its own, print out some things. So there's a one-to-one isomorphism between the set of graded Artinian Gernshtein quotients having self-degree J and the forms of degree J in the dual algebra, the S, equals K of X1 to Xn, capital X, mod multiplication by K star. So the isomorphism is that the algebra is the ring R divided by an ideal, which is the annihilator of F. And that corresponds to F mod the multiplication by K star. And also, if I look at the differentiation action on F, that gives you a vector space. It's actually a module over A, which is the dual of A with the same Hilbert function. The dimension of K of Ri, oh, that's always a mistake. It will go away perhaps in a second. So here's an example. This example comes from a famous example of Stanley about what's called Nagata idealization. So the ring R is K of XYZ U1 through U10. And S is the capital of variables. And you write mu1, I'm sorry, that should be mu1 through mu10 in the first ring, sorry. You write mu1 equals x cubed and mu10 equals z cubed for the 10 degree 3 monomials in XYZ. And you take F is the sum of, from I equals 1 to 10, of a new variable, capital U sub I, times that monomial mu sub I. So that's a general procedure of this Nagata idealization. You take actually a level algebra usually, and look at the dual generators, and you multiply each one by a new variable, and look at the F. And then what happens is that when you look in this particular example, is that when you look at the annihilator of F, the Hilbert function comes out to be 1, 13, 12, 13, 1. And this is not going to be weak Lefschetz, or it won't be strong Lefschetz, because the map from degree 13, I'm sorry, from degree 1 to degree 3, multiplication by L squared, just cannot be an isomorphism because it has to pass through degree size 12. So the reason why it's 12 is that if you look at the XYZ, that vector space times U1 through U10 circle F, that lands inside a K of XYZ. That should be capital XYZ. That's my mistake there. In degree 2, that's a dimension 6 vector space. The reason is that these small UIs are canceling the capital UIs in the F. And if I look at K of XYZ in degree 2, circle F, that's also 6, or certainly not more than 6, because K of XY and Z in degree 2 has 6 elements. So that R2 circle F is a direct sum of both those, and the dimension is 12, cannot be strong Lefschetz. Now here it turns out that the partition, if I use a generic linear form, is what you see on the left there, 5 copies of 3, 6 copies of 2, 8 copies of 1. It's very far from even the best you could do if PC of H, if you assume that you have that Hilbert function. You imagine what you can do. If you look at 1, 13, 12, 13, 1, you can think of, oh, I have room for 1, 1, 1, 1, 1, a string of length 5 starting in degree 0. And then I have a room for 11 strings of length 3 starting in degree 1. And then I have two left over, 1 in degrees 1 and 1 in degree 3. So the best I could do with that Hilbert function is 5, 11 copies of 3, and 2 copies of 1, even imagining that I could achieve that. So this is a famous example. It's the first example where there was a non-unimodal Hilbert function. So here's another example that's unimodal, but it turns out that, so this is a similar, because let's see, it's not quite the same. It's not a, because we're taking WXY and we're doing, some kind of combination that's cute. And then the Hilbert function is 1, 4, 10, 10, 4, 1. But the multiplication from A to A3 is not an isomorphism. That means the partition, you have one string of length 6 going from degree 0 to degree 5. And then you have 3 strings of length 4 going from degree 1 to degree 4. And then you have 5 strings instead of 6 of length 2 going from degree 2 to 3. And then there's, because that's not an isomorphism, there's a 2 strings of length 1 in degree 2 and in degree 3. So this is not even weak Lefschetz, but actually not being weak Lefschetz, it's still very close to the strong Lefschetz, which would be 3 copies of 4 and 6 copies of 2. So that's Mikeda and Sakaguchi. Oh, no, sorry, it's Ikeda who became Sakaguchi. Her first name was Ikeda. Let's see, just what did he do? Oh, so here's another example, which is similar, but now it's closer to a Nagata idealization, because you have these variables u1 through u2, u3, u4, multiplying some monomials, and this is not of degree 2 in x, y, and z. So the Hilbert function here turns out to be unimodal, but does not have the weak Lefschetz property, because the map from A1 to A2 is not injective. And this is a little bit of information about the ideal. So there's a way of looking at this using Hessians, but I will just briefly mention a little bit later, but this proof involves some geometry and some Hessians. So I'd like to introduce now formally the Jordan degree type. So all that it does, as I said, is appends to the Jordan type the initial degrees of the strings. So in 2 variables, if I take a general enough linear form, it's always strong Lefschetz. So when the Hilbert function is 1, 2, 2, 1, 1, as it is for this algebra, its vector space basis is 1, x comma y, and then y squared and x squared, and then x3 and then x4. The Jordan degree type of L equals x plus y, that's general enough, is going to be the strong Lefschetz value, but with a string of length 5 beginning at degree 0 with 1. And then that string is 1L up to L to the 4. And then be a string of length 2 starting degree 1, which would be y and yl. In this case, yl is the same as y squared. Of initial degree 0 and 1. But if I look at multiplication by y, then since y cubed is 0, I can only get a length 3 string. So it turns out that there you have the length 3 string 1y and y squared, and then each power of x gives you from degree 1 to 4 gives you a single string of length 1. And so that notation 1, up arrow 1 to 4, indicates that there is a series of strings of length 1 from each degree from 1 to 4. Now, I'm introducing one invariant, the multiplicity of the NV in the Jordan degree type. So if I looked at strong Lefschetz Jordan degree type for this Hilbert function, there'd be a 7 degree 0. There'd be two length 5s beginning degree 1. And then there'll be 2 length 3s beginning degree 2. And so the multiplicity of 5 in degree 1 and the 3 in degree 2 is 2, because there's 2 of them. And that has to do with those differences. 3 minus 1 is 2. 5 minus 3 is 2 in the strong Lefschetz. Now, it's an interesting result. It's really from a result of Harima and Watanabe, Chetsu Watanabe. It's also, we wrote it in our survey about Artinian, and with Pedro and Chris, Pedro Macias Marquez and Chris McDaniel. And it's also a lemma in a paper of Costa and Gondin. But it really relies on an initial work of Harima Watanabe on central simple modules. So it's just that the Jordan degree type is symmetric for an a graded Artinian Gorenstein algebra. So that's very pretty. And here's the formal statement, but let's see if we can make some kind of a example for it. So all that means is that when you view it, view the Jordan degree type, it's got those strings have to be symmetrically placed around the middle J over 2. So let's see. It turns out the Jordan degree type is a finer invariant than the Jordan type. So this is a little bit of a technical example, but it's in codimension 3. We put it in our survey. Actually, it's new. It wasn't. So here's the Hilbert function. So, excuse me. Have a glass of water. I'll take another sip. So, there's 2 algebras, A and B, and the ideals are given below. And the first algebra, if you look at the Jordan degree type, it is 3 in degree 0, 2 3s in degree 1, etc. 3 in degree 2. And I did this instead of using the short notation, which would be 1 from 2 to 5. We wrote them all out. And so notice that the ideal, well, let's see. So W is this vector space 1z z squared. And I'm making A to be a certain structure that depends on W. That's a vector space. So it's that A consists of W, X times W, Y times W, X, Y times W, and then the set of powers of X from 2 up to 5. There's an ideal defining it, and that ideal is given to you right there. Y squared X, Y, Z, X squared, Y, Z cubed, X 6. There's a, this is not Gorenstein's. So there'll be several dual generators. There'll be 1, 2, 3, 4, 5. There'll be 1 in degree 5, and then there'll be at least another one in degree 3. So actually 2 more in degree 3. No, at least 1 more, sorry, in degree 3. But then B looks a little different. B looks like W, X squared W, X cubed W, and some powers of Y. So you can see that structurally, A and B are somewhat different. And in this case, the Jordan degree type for B is certainly different from the Jordan degree type of A in that the 3's are rearranged and the 1's are rearranged. But it has the same number of 3's and the same number of 1. So the Jordan types are the same. And let's see. I'm looking at the Jordan type, and I didn't put this in the screen, and I think it must be the Jordan type with respect to Y. Yes, because the Y time, no, yes, because it's a Y squared, so I'm allowed to have a 3. So this Jordan types out with respect to Y. If it turns out you use a linear form X plus Y plus Z that's generic, it turns out that these are strong Lefschetz. So in discussing Jordan degree type or Jordan type, I'm interested not just in generic linear forms, but also arbitrary linear forms. So here's another example, which is from Nazreen Al-Tafi, who just completed a doctoral at Stockholm at KTH. It has this Hilbert function 136999631. It has the two dual generators involved are, let's see, are capital F and capital G. They look a little different, and it turns out that the Jordan types are the same. 3 copies of 7, 4 copies of 4, 2 copies of 2, 6 copies of 1, but the Jordan degree types are different. In the way you see there, the 2's occur in different degrees, and the 1's occur in different degrees than the 1's in the A and B. The 1's occur in different degrees. Now this is checked using a method Nazreen kind of introduced using rank matrices. The rank that depends on Merkel-Jinso and Harima, but it's nicely phrased in what Nazreen does. So here's some questions on Jordan type or Jordan degree type. The first question, for which Artinian algebras is PL equal to HAV? Well, here you could take a generic L. So this is really well surveyed in the Springer lecture notes number 2080 and a paper by Miliari and Nagel, at least up to maybe some years ago. All codimension 2 Artinian algebras are strong Lefschetz in characteristic 0 or characteristic bigger than the Sulkel degree. It really depends on a result of Joel Briançon in 1972, although it's ascribed to, I think it's been rediscovered by at least 7 different people who each feel that they are the originators. All graded completing sections in codimension 3 are weak Lefschetz. That's a subtle paper involving vector bundles by a group including Miliari, Watanabe, I think Nagel, and others. But a major question, in a certain sense, is which graded Artinian Gorenstein algebras in codimension 3 are strong Lefschetz? And there's some either bold or reckless people who think that all of them should be strong Lefschetz. But in the context that all that can be shown so far is that graded completing sections in codimension 3 are weak Lefschetz using a strong tool, namely vector bundles. I I find this question, I'm more interested in what are the counterexamples of what, which ones are. And there is a guess that, well, let's see if I get the result of Nazreen. No, let me go back. So there's a paper by Nazreen on strong Lefschetz where she shows that if what's called a tight annihilating scheme, which I think I'll mention a little later, is a bunch of smooth points in general position, then in any number of variables, the related Gorenstein algebras are strong Lefschetz. So that suggests that the answer might involve when there's what I call a tight annihilating scheme. Let's see if I get to that. So this is a question, if you solve it, you'll be very popular among the commutative algebraists, even in special cases, or if you find a counterexample. So there's work by many which is very deep, which I'm not really strongly familiar with, but on Hodge-Riemann relations. This is over the reals, and strong Lefschetz for algebras related to the simplicial complex of the matroids. And there's some very good references on this and excellent papers. And this was kind of started by a paper by Prazito, Junho, and Katz on the Hodge theory for combinatorial geometries in 2015. There's recent papers by Ardila, Denham, and Hu also in 2020, and a very recent posting by the group of people in 2020. I think I'm intrigued whether any of these things work in characteristic P. I mean, the Hodge-Riemann seems to be very strongly involved in the reals. So my question might be, what extends? For all I know, actually, I don't know these papers really well, so conceivably, one of them really did look in characteristic P, but my hunch is not. Here's some earlier papers on the strong Lefschetz in combinatorial settings by Mino and Numata, by Cook, Junke Kubica, Satoshi Mirai, and Erin Nevo, and by Kubica and Nago. So that's an interesting, I think, could be a rather deep direction to go. So question B, which Jordan types occur for a given Hilbert function? In other words, I fix a Hilbert function, I allow all L, not just generic ones, all linear forms, and then I ask for what can happen. So in two variables, continuous sections, Nazreen, Leila, Katami, and myself wrote a paper which answers that question. In two variables more general, Nazreen, Leila, Joaquin Yamego, and myself wrote a preprint, which is on the archive, that answers the question. But that kind of question is open for Gorenstein sequences in, for example, 3 variables. And a group of us are looking at that. And I must say, despite having a Pfaffian structure theorem of Buchsbaum and Eisenbach, it's absolutely amazing that with such a strong structure theorem, one knows so little. There's a question about comparing the Jordan type with the conjugate of the Hilbert function, or there's an analog for Jordan degree type. Is PL less equal to the conjugates, in the dominance partial order, which I think I'll have a screen later, and the answer is yes for A graded and L being an A1. It's also yes for A local if L is in the maximal ideal. Whoops, I think I'm going from B to D. Nope, I'm going from C to D. It's okay. So one question, behavior on the tensor product, and on free extensions or connected sums. We'll discuss the first of those a little later. And E, which pairs of Jordan types can occur in the same algebra? So let me say that E and E prime are very deep questions. I call it thorny. That means that thorns, like in rose bushes or maybe cacti, about commuting nilpotent Jordan types, where extreme basic questions are open. And those of us who have looked at least feel that we get some very pretty diagrams and examples, but there's a hidden structure underneath which we don't really understand. So I think that's a very interesting area, and there's some references. There's some results that are known. For example, there's a question about maximal commuting Jordan types, Q of P for P. Well, that means you have two matrices that that are Jordan types, and they correspond to well, the matrices that commute. And so I'm interested in what's, if I fix a Jordan blocks for one matrix P, what's the maximal Jordan blocks in the maximal commuting Jordan type in the dominance order for something that commutes with P. And this is known, the answer is known when the QP has less equal to 3 parts by work of Polona Oblak and Leila Katami. And the fact is, the parts of QP differ pairwise by at least 2. That's a work by Polona Oblak and Thomas Kosier. So free extensions. Let's see how we're doing on time. We're about halfway through, and we are more. So I will skip some of the material on free extensions. It was introduced by Junso Watanabe and T. Harima. The notion, it may have been, may have some historic beginnings. It's basically a deformation of the tensor product. So so C, well, that's a theorem from Chris, Pedro, myself, and a referee who really supplied an important piece. Could have been someone here. A free extension with fiber B is a flat deformation of A tensor B as an A algebra. Not all flat deformations are free extensions. And then you have, as a consequence, that the Jordan type for a generic linear form of a free extension is bigger than or equal to the Jordan type of the tensor product, because Jordan types behave well in the dominance order under deformation. So these are some specialized results of the kind that can be somewhat technical and subtle, even though the statements are fairly clear, and maybe it'd be better for if people are interested, look at the notes or the slides rather than for me to go through every piece. That's if you assume that the Hilbert functions of both A and B are symmetric, and that both A and B are strong Lefschetz, then the free extension or the tensor product is strong Lefschetz. And so we found a counterexample to a conjecture of Junso Watanabe. Even if A, B, and C are standard graded with symmetric Hilbert functions, the free extension itself being strong Lefschetz does not imply that the pieces are strong Lefschetz. So we take an example due to Perazzo from, I think, 100 years ago. And here's the dual generator. It's another Macaulay idealization. And the Hilbert function is 1551. B is not S strong Lefschetz. That was the example we had earlier in slightly different notation. But C, the tensor product is. The free extension is. All right, so I want to say a little bit about tensor product. There's a Clebsch-Gordon theorem, which determines the Jordan type in a tensor product of, you take a element A, a linear in the first algebra, then an element B in the second algebra. You want to find the Jordan type of the A tensor 1 plus 1 tensor B, and there's an answer, at least in characteristic 0, or characteristic bigger than the Sokal degree. And this is the answer. It's once you know that for example, if this M with a bracket by mean k of x divided by x to the n, and the n I can look at it as k of y divided by y to the n. And if I took the tensor product of those, that's k of xy mod x to the n, y to the n. But if you look at the Hilbert function of that, 1, 2, 3, 4, up to m, and then where m is a smaller, and then it cuts down by 1 in degree n and goes down, then it's pretty clear that it's the strong Lefschetz Hilbert function is m plus n minus 1, m plus n minus 3, etc., and in n2 or 1. For example, 3 tensor 3 is 5, 3, 1, 3 plus 3 minus 1, etc., going down by 2. And in general, to obtain the Jordan type of tensor product, you take the tensor product of the two partitions. So 3, 1 tensor 3, 1, you have, oh great, I did it again. So you have the 3 tensor 3, which is the 5, 3, 1. You have 3 tensor 1, which is just a 3. You have a 1 tensor 3, which is just a 3. And then you have the 1 tensor 1, which is a 1. But you had one extra 1 from the 5, 3, 1. So it's cute, but and very useful. There's a let's see. There's some results. If A and B are standard graded with symmetric Hilbert functions and strong Lefschetz, then the tensor product is strong Lefschetz. The converse is open if you do not assume that the Hilbert function is symmetric. The assumption that H and A and H and B is symmetric to get that the tensor product is of a two strong Lefschetz is strong Lefschetz is necessary because of the counterexample of Migliore, Nagel, and Schenck, which you can find. It's just a very simple example. You take the tensor product of k of xy divided by the maximal ideal squared. So this is the dominance partial order that I mentioned earlier. Should I take 50 minutes or 55 minutes?
1 hour. It's a 1 hour talk. Then we will have a discussion.
Okay, that's what I have original time. So dominance partial order is you sum up the first k parts of a partition, and you ask that it be, the partitions are the same number, and you ask that the sum of each, for each k, the sum of the first k parts of the first is at least that of for the second, and in that case p is greater equal to p prime. The theorem is if A is graded and L belongs to AI is homogeneous, then PL is less than the H of A, the conjugate in dominance partial order. It's open whether actually, and whether this is true if we allow L to be in the maximal ideal. That's a bit striking as an open question. In a case of a local Artinian algebra, then PL is always less equal to the Hilbert function conjugate. The local algebras don't have a symmetric Hilbert function in general. Even when they're Gorenstein. Okay, this talks about the modular case where you take low characteristic and look at the algebra k of x, y, mod x to the m, y to the n. That's basically a tensor product. And this has been studied a great deal. We tried in the Artinian survey or article to mention 3 different lines of people who have studied this. Namely, people in representation theory, Gillespie and Prager, people and others doing Keiichiro Ima and Ryo Iwamatsu doing shear functions. Renault was one group, but there's some theorems. Gillespie et al. Says that A of Mn, that ring, and characters k equals p, is always weak Lefschetz. It is strong Lefschetz in the following situation. And then there's a sort of technical theorem involving deviation vectors. So this doesn't answer the full question about the Jordan types. But Nicklason in 2018 completely answered when A of Mn is strong Lefschetz mod p for each triple using base p expansions of M and N. So we don't really know the Jordan degree types when it's not strong Lefschetz, but we do know when it's strong Lefschetz. So I think that's an interesting area that's been studied by these different types, groups. Jordan type of higher Hessians. Without defining the Hessians, that has to do with the cataleptic matrices when you substitute in the linear form. So it's a matrix you make out of A and B are elements of degree I and J minus 2I. A are elements of I and I. I take A, B, circle F, and I take a determinant. But the relevance is you have a geometric object, the Hessian, a matrix, which you evaluate at some points. And the map that goes linear form to J minus 2I from A sub I to capital A J minus I has rank equal to that of the that appropriate Hessian evaluated at the point that corresponds to the linear form. In particular, the linear form is in J minus 2I is an isomorphism is equivalent to that Hessian not being 0. So the point corresponding to linear form summation of AI small xi is the point PL equals the coefficients of those forms. So this converts questions. This is relevant to Artinian Gorensteins involving strong Lefschetz or possible Jordan types into questions about ranks of Hessians. Here's an example. I think I want to leave that formally for the notes. If you look at x4 plus y4 plus z3x plus y, the neither is this. The matrix K1F, which has to do with a map from degree 1 to degree 3, is this matrix that drops rank when I plug in 1, 0, 0, 0, 1, 0 to 1. And at the points 1, minus 1, 0, and 0, 0, 1 to 2 rather than 3. And so this, for example, looking at the 0, 0, 1, says that the strings multiplication by z on a, well, that's 1z, z squared, z3. The partition is 4, 1 to 4, but the rank of z to the cube from a1 going to a3 is that same 2, corresponding to the 0, 0, 1 when I plug in 0, 0, 1 to the matrix. Let's see, does that make sense? Yes. I plug in 0, 0, 1, I get zeros in the upper left corner, 2 by 2, and I get ones in the bottom and on the right, and that's a rank 2 matrix. So here's another set of questions. What sets of partitions are possible if I'm giving the the partition P sub A where A belongs to the maximum ideal of A. The compatibility question we've already discussed. Given partition P prime of N, can we find algebras A, elements in them with the partition? What is this going on? I'm going to have to disconnect this. Oh, what's going on? But there. Sorry. My printer's decided to be imaginative on its own. So in this one, this is this question of commuting nilpotent pairs. One example is that 4 and 3, 1 are impossible in the same Artinian algebra. They don't commute. This is results of Oblak-Kosier and a group, Leila Katame, Van Startikum, Ruizal, and myself. Question 2, for which Artinian algebras does a generic L give a partition that's weak Lefschetz but not strong Lefschetz? And there's been a substantial work by Gondin, Mazzetti on giving examples and results in this direction. So what I like about this is it used to be that people just talk about weak Lefschetz and strong Lefschetz. And what I have always wanted to say is that those are really very limited cases of the invariant you can get. Weak Lefschetz just means you have the right number of parts corresponding to the biggest height of the Hilbert function. Strong Lefschetz just means that you have it's much more precise. It says that the Jordan type is the same as the conjugate of the Hilbert function. But in between, there's a lot of possibilities. And these have been more stated in the last few years. This one, I'll give you a Jordan type, characterize which Artinian algebras have that generic Jordan type. Fix the Hilbert function 2. One's a locus questions. Attached to the Artinian algebra, you can make a projective space, and then you can make a locus in that projective space of the A inside the maximum ideal such that the partition, the Jordan type for A is equal to the P. Invariance, obstruction to deformation, and I want to, okay, free extensions. This is good for the notes. I want to mention this last application as my last piece today. This is joint work with Pedro Macias Marquez. So we consider non-homogeneous Artinian-Gorenstein algebras. That means that the Macaulay dual generator is a polynomial and not just a homogeneous form. I've always found it convenient to play with Artinian-Gorensteins using the dual generator because you have a single piece, a single object, a polynomial, which is known only up to the partial derivatives. So it's not just a polynomial, it's a polynomial mod action by differentiation, by differential units. But still, you have something very physical and very, I can see it. So there's a theorem which of mine some time ago that the associated grade algebra A star has a finite decrease in filtration, such as the sets of quotients are reflexive. A star modules with centers that shift. The Hilbert function of a non-graded local Artinian-Gorenstein is not symmetric, but it has a symmetric decomposition given by the sum of the Hilbert functions of these successive quotients. So here's an example. I look at the dual generator x4 plus y squared. The another ideal is small xy and then y squared minus x4. You can see that xy is acting gives 0. That's partial respect to x, partial respect to y if you want. Y squared acting on capital Y squared is 1, minus x4 on capital X4 is minus 1, that gives you 0. You're in two variables, so a Gorenstein ideal must be a complete intersection, so this is it. The Hilbert function is 1, 2, 1, 1. And if you look at the A star, it's R mod xy, y squared x5, the associated graded. Q0 is always the algebra that comes from the highest degree term, capital X4 in this case. So the neither of x4 is y, and you have to include x to the 5. So the Q0 is R mod y to the x5 with Hilbert function 1, 1, 1, 1, 1. Q2 is, turns out to be y x5 mod xy, y squared x5, which is just the vector space y. And the Hilbert functions of those are 1, 1, 1, 1, 1, and 0, 1, 0. And you have the Hilbert function 1, 2, whoops, what did I do here? Oh, there's an extra 1. So there's a mistake in the Hilbert function of A. It should be 1, 2, 1, 1, 1. So if you fix that mistake and you add up h of 0 and h of 2, you get the Hilbert function of A. Sorry for that mistake. X plus y strings, it's 5, 0, 1, 1. So here's a result that that we found, that if you look at this Hilbert function, which is not symmetric, but it occurs for Gorenstein Artinian algebras, here are three different Jordan types corresponding to this Hilbert function. One comes from, I give an example. We give an example of each one. X3 plus Y3 plus C3. Here's the Hilbert function 1, 2, 3, 4, 1, 2, 3, 4, 3, 2, 1. H of 3 is 0, 1. If you always, when you add these together, if I made no mistakes, no, that's okay. You get H of 0 plus H of 3 is equal to the original H up there. The first one has Jordan type 7, 5, 3, 2, 1. D2, gives you Jordan type 7, 5, 3, 3. And D3 gives Jordan type 7, 5, 4, 2. Now, if you notice, in the dominance order, the biggest Jordan type is P3, because 7 plus 5 plus 4 is bigger than 7 plus 5 plus 3. And P2 is bigger than P1 because 7 plus 5 plus 3 plus 3 is bigger than 7 plus 5 plus 3 plus 2. So in terms of specialization, I can only specialize, provided I have a generic enough element in each, from the C, from the D3 to the D2 to the D1. On the other hand, so that's given by the Jordan types. On the other hand, there's another stratification which comes from the H of 0. And it turns out that I can only specialize from a bigger H of 0 to a smaller H of 0. You can understand that because H of 0 has to do with the biggest degree term in the dual generator. So I can only specialize from a higher number of partial derivatives to a smaller. So I can only specialize from D1 to D2 to D3 if I have a generic elements. The consequence of these two statements is that we have three irreducible components. We thought that was, well, I've been interested in the irreducible components of the family of Gorenstein algebras of a given Hilbert function for some time. And this was an example which was interesting, where we could actually use a Jordan type. That's my end. Thank you. These are some reference papers. That's all I have to say.
Thank you very much. For a very interesting talk, presenting many concrete examples and many questions. We can now entertain questions from audience. You can open your mic and ask questions directly.
let's see. Okay, I'm here. I should have answered all questions. There should be no.
Well, you have presented many interesting questions. Yeah. Yes,
Let me
Marina.
camera. Okay.
Hi.
Yeah.
Good morning, Tony.
Good morning.
Everybody. I have a question, very basic, maybe, concerning the Jordan type. My question is, if you fix the star decomposition, no? Concerning
The first link.
the last slide, the symmetric decomposition. Then you fix the Hilbert function. Then you fix one decomposition.
Oh, sorry. What was that? I don't think it's me. Okay. Yes, I'm gonna fix one decomposition.
Yes, in this case, the Jordan type is completely determined, or you can have more Jordan type.
So the answer is you can have more Jordan types.
Yes.
So the there's always a generic, of course,
Yeah.
Which you can't immediately get from the decomposition Hilbert functions, because they can differ. So that's another subtle part of it that that actually Pedro and I are looking at, and hopefully we'll have something out. We have a paper started, but so the question is, if you fix a decomposition, symmetric decomposition with Hilbert function, does that tell you the Jordan type for linear forms? It tells you it will. There's certainly a generic. Well, actually, it's open even whether if you make a symmetric decomposition, is that a irreducible family? So I think the answer would be certainly yes for 3 variables. But in more variables, I would expect that you can't even say generically, because there'd be several components. But always you can make very special linear forms that will give you different answers.
When you say generically, means the Hilbert function for corresponding to a generic polynomial, or what do you mean?
I meant generic linear forms. So I'm going to fix. Okay. I'm going to fix a symmetric decomposition, and then and maybe and then ask what happens for a generic linear form, and something strange. Oh, okay. So yeah. So certainly there'll be some situations, like in 5 variables or something like that, where I have a Gernshtein Hilbert function, non-symmetric, where there's several irreducible components, and where on each one there might be a different generic Jordan type.
I understand. My question was because I was interested in Jordan type in order to classify, to find the Hilbert function of the complete intersection. And then I would like to see, because in your monography, your guess is that in the case of a complete intersection, you have only one star decomposition. This is not true, but
wait a second. Could you say again that statement? So what you say is, I claim. Yeah.
My curiosity was because I was interested in the Hilbert function of a complete intersection, for instance, in 3 variables. In 2 variables is known. In 3 variables, we don't know the shape of the Hilbert function of a complete intersection in the local case.
Yes, I agree.
In not grid case. And my question concerning the Jordan type was in order to understand if the Jordan type could be useful in order to study this kind of problem.
I would hope so. I do think it's an outrageous problem that given the books on Eisenberg's structure theorem with Pfaffians, one cannot figure out even whether actually that doesn't tell you more information. Completed intersection already. The books the Pfaffian decomposition tells you nothing. But even the complete intersection, you can find you don't know the Hilbert functions.
You're right. You're
absurd. So it's great that you're looking at it.
Thank you, Tony.
Any other questions? So in the last example that you presented, where the graded algebra was not standard, but and so Hilbert function didn't turn out to be symmetric, but it is a sum of symmetric. I mean, Hilbert functions of some other algebras, and they are symmetric. Is it always true?
Yes. So that's the theorem of the memoir, AGA, Associated Graded Algebras, that I wrote some in, it was 1996 or something.
Okay.
So it's that if you have a Artinian Gorenstein algebra, then the associated graded algebra has a stratification whose quotients are reflexive modules over the A star. And that just comes from being Gorenstein. And you can't tell it just from A star. In other words, if you know A star, the associated graded algebra, you don't know this stratification. But it always exists. And so I can always write the Hilbert function of A as a sum of shifted symmetrics. In the case of two variables, there's no extra information. The shifted symmetric is determined by the Hilbert function. But in any more variables, and we're talking about, then there's more information.
Thank you.
I talked to Johanna in about an hour, so see if she has questions. She can ask.
Yeah, John. Yeah, you have questions, Johanna? Well, there are so many questions and interesting examples to experiment with. Yeah, but what is intriguing is, to begin with, you write an algebra, a polynomial f, and then many things happen. How do you find that polynomial?
That's an extremely deep and hard question. So even a completed section, that's been a hard problem for people. So the simple way is you put it you put it into a computer, and you look at the Circle degree, and you look at what annihilates in that degree, or you look at the polynomial that's annihilated by all the ideal. But there's really not much known about how to find that from say the generators of the algebra, except by doing what I said, which is you write it, you look at the ideal generators, you look at the Circle degree, and you play around and you find. So that's a good question.
This construction goes back to Macaulay. This construction of studying the Gorenstein algebra using annihilator of a single polynomial.
It certainly goes back to Macaulay. It might even go back earlier, but Macaulay in his 15 called inverse systems, described this, and then in later papers he said more about it. But he used different language than we use. He didn't have the word Gorenstein ideal, but he has principal system, that's a Gorenstein. Then he had one for complete intersections. So there's a language in that book, which when that was updated by the algebraist at there's a new version of that which had a little bit of a translation.
Right. Paul Roberts
That's
gave
right. By Paul Roberts,
introduction with new. Yeah, he explains many things, and I should go back and look at that once again.
Yeah, he was really helpful.
It's amazing how Macaulay could think of so many things
Yes,
alone and so early. It's really amazing.
yeah, I agree.
Even things like linkage, and they all go back to him.
Yes, I agree.
Right.
Although I think some linkage may have been around earlier. Do you think?
I mean, in the geometric situation, yes. Yeah.
Yeah.
Right.
Hi, Pedro. He's one of the complicit people in this.
You gave reference to work of Adi Parajito and Jun Hu.
Yes,
and other people which involve metroids and other things.
Yes, I think that's very deep work and very it's somewhat astounding and something which I would love to learn more about. So really, that's something.
Karim, when he was a student, he spent a semester in our department.
Oh wow!
Yes, yeah. He took some advanced courses, and I mean, lots of people from Europe come. They are very curious about India in general.
Yeah.
Right. So he spent a semester. I remember he attended my course, and it was interesting to talk to him. But I have not met him after that. Yeah. Now he's doing such deep and very interesting work.
Yeah. Actually, Joanna is a student of his.
I see.
Indeed.
I see. Okay.
Yeah, he's mostly in Copenhagen now, partially still in Jerusalem.
Okay. Well, next year I want to remind him to come back online at least to Mumbai. Right. Yeah. Okay, so I guess I don't see any further questions.
I have one question. Can you hear me?
Yes, yes, yeah, please.
Yeah. Sir, you remarked that there is a notion of Lefschetz properties in the local setting also. Can you give some reference for that?
For the decomposition, symmetric decomposition?
No, not symmetric decomposition. Regarding the Lefschetz properties for the local algebras. Strong Lefschetz properties for local case.
That's a good question. I would say the preprint that Pedro and I are working on might be a source, and it might be the only source that I know of. So I think there's a lot of open questions, and if you want, when we get the preprint in a readable form, which is probably probably a month or two.
Okay.
Then we could. So there's a lot of questions, and
okay, it is not still an archive.
No, it's not an archive. We went there. No, I mean, we saw the fixed things. There's some results. What we might do, if you're interested, is ask you to look at it at a certain point when we feel it's a little more readable, and make some comments.
Okay, sure. Yeah, thank you.
Okay.
So, thank you, people, again, and I think it's great that during this COVID pandemic, people can get together and have a seminar. I really appreciate it.
We hope to continue even beyond this. This is one positive point of the COVID. Nobody expected this. We can get together and we will continue this seminar, not so regularly, but as we find more speakers.
Great.
But fortunately for next year, we have all seminars fixed up to September.
Oh my gosh.
Yes, yes, yes.
Wow.
People are very enthusiastic because they are feeling lonely. And
Uh-huh.
so even I found it surprising that speakers are also feeling, I think they are feeling more lonely. They want to talk, right?
Yeah, sure. And
So,
actually, I must say the speakers get a great advantage. If I'm preparing a talk, I said, oh, gee, what about that? Which I hadn't thought about before. And
right,
so I think it's a great service to the speakers as well.
right. It focuses your thoughts. And
Yeah. So I'd like to
right.
thank Pretty also for training
For
me.
the students, it's a blessing because they are all alone at home. And, this way, I think we are producing a large number of open questions. And I hope we all do some good research even after this. And so thanks a lot, Tony, for coming online. It was great to have you. And thanks for bringing all the interesting examples and open questions. And this is what a beginner is always looking for, in a difficult subject which has been investigated by so many people. Yeah. So thanks a lot. And we will close the meeting now, and we hope we will have you again sometime next year. Yeah. Thank you very much.
Thank you.
Thank you.